Welcome to the Geologic Time Lab. This week, our activities, content, and assignments will help you be able to do the following. 1. Understand how isotopes and principles of radioactive decay can be used as an absolute dating technique. 2. Collect, graph, and analyze data to solve problems concerning radioactive decay. 3. Use principles of relative dating and stratigraphic correlation to resolve the depositional and geologic history of a cross-section. 4. Become familiar with the geologic timescale and how Earth scientists made it. And 5. Determine ages and order of events based on incomplete data. First, we'll start with some background information to provide you context for this week's lab. Time is one of the most basic examples of something that is socially constructed. We collectively create the meaning of time. It has no predetermined meaning until we give it meaning. To say that something, like time, is a social construction is not to say that it doesn't exist or is merely an illusion, but instead that humans have created systems of meaning that creates the concept of time. Because time assumes such significance in human consciousness today, we have developed elaborate tools to measure it and formal scales to record it. We use a second as a basic unit of time measurement. What exactly is a second, though? From 1900 to 1968, we defined the second as 131,556,925.9747 of the year 1900. But now we define it as the time it takes for a cesium atom to change back and forth between two energy states 9,192,631,770 times. This change can be measured with a device called an atomic clock, which has an expected error of only about 1 second per 30 million years. We sum 60 seconds into 1 minute, 60 minutes into 1 hour, and 24 hours into 1 day, about the time it takes for Earth to spin once on its axis. The geologic timescale is a chart of named intervals of the geologic record and their ages in both relative and absolute time. It has taken thousands of Earth scientists from all parts of the world more than a century to construct the present form of the geologic timescale. Earth scientists tell time based on relative and absolute dating techniques. Relative age dating is the process of determining when something formed or happened in relation to other events. For example, if you have a younger brother and an older sister, then you could describe your relative age by saying that you are younger than your sister and older than your brother. Absolute or radiometric age dating is the process of determining when something formed or happened in exact units of time, such as days, months, or years. Using the example above, you could describe your absolute age and your sibling's age by saying, I am 19 years old, my brother is 17 years old, and my sister is 22 years old. As a reminder, everything in the universe is made up of atoms, which are the smallest unit of elements. Atoms themselves are made up of subatomic particles, including protons, neutrons, and electrons. The protons and neutrons exist in the middle of an atom, which is known as the nucleus. The electrons orbit around the nucleus. Atoms of the same element that have different numbers of neutrons are referred to as isotopes. Isotopes of an element vary in atomic weight, mass number, but not in atomic number, or the number of protons. Radioactive isotopes are used to determine the absolute ages of Earth materials. Radioactive or parent isotopes decay over time, transforming into stable or daughter isotopes. This process is known as radioactive decay. The parent and corresponding daughter are called a decay pair. Earth scientists then measure the ratio of parent to daughter isotopes to determine the age of a material. Atoms of a parent isotope will always decay at the same exponential rate over time to the same daughter isotope. This constant rate is what makes absolute age dating possible. The rate of decay can be expressed in terms of half-life, which is the amount of time it takes for half of the parent atoms in a sample to decay to stable daughter atoms. When selecting a decay pair to calculate the age of geologic material, it is important to note the half-life of an isotope. After 5 or 6 half-lives have passed, there is not enough of the parent isotope left to make an accurate assessment of the decay rate. There are approximately 350 naturally occurring isotopes, some of which are stable, meaning that they are not radioactive and do not decay over time. Radioactive isotopes are unstable and decay spontaneously at a regular rate through time. For example, the parent isotope, carbon-14, is unstable and decays to the stable daughter isotope, nitrogen-14. This is a quick summary table of radioactive decay that you can use as a reference to determine the age of Earth materials. This will come in handy when completing your lab. Probably the most famous application of absolute age dating is calculating the age of our planet. Earth's age was determined by Earth scientists that use radiometric dating to calculate the age of zircon crystals from the Jack Hills in Western Australia. The decay pair measured was uranium-238 to lead-206. Next, we'll practice absolute age dating with a few practical applications. The dinosaurs first appeared roughly 230 million years ago and went extinct 66 million years ago. Which decay pair would you use to date a dinosaur bone? To answer this question, we must find a decay pair that can date material between 66 and 230 million years old. Because carbon-14 is present in all living organisms, you might be inclined to choose this isotope. However, the half-life of carbon-14 is only 5,370 years, meaning that any material older than 60 to 70,000 years old cannot be dated using carbon-14. The 3 decay pairs that can be used are uranium-238 and lead-206, uranium-235 and lead-207, and potassium-40 and argon-40. A volcanic intrusion contains zircon grains with uranium-235 lead-207 ratio of 46.62. How old is this intrusion? We can find the age of this intrusion by multiplying the half-life of uranium-237 by the number of half-lives that have already elapsed. First, we'll use the table of isotopes used for absolute age dating to find the half-life of uranium-235, which is 713 million years. Next, we'll use the second table to find the number of half-lives that have elapsed based on the parent-daughter ratio of 46.62, which is 1/32, or in decimal form, 0.031. We can then multiply these two numbers to find that the igneous intrusion is approximately 22,281,250 years old. A paleontologist discovered a fossilized mammoth bone that contains 12.5% of its parent, carbon-14. How old is the bone? We can find the age of the fossilized mammoth bone by multiplying the half-life of carbon-14 by the number of half-lives that have already elapsed. First, we'll use the table of isotopes used for absolute age dating to find the half-life of carbon-14, which is 5,730 years. Next, we'll use the second table to find the number of half-lives that have elapsed based on the 12.5% of remaining parent atoms, which is 3. We can then multiply these two numbers to find that the fossilized mammoth bone is approximately 17,190 years old. Frequently in earth science, absolute age dating is not a very practical means of determining age. One of the limitations is the time and funding necessary to collect appropriate samples and analyze them in a laboratory. It isn't very accessible because it typically requires a team of scientists with specific and sometimes uncommon expertise. Finally, not every isotope can be used, and not every rock can be dated. Because sedimentary rocks are made up of other rock fragments, an age of the rock cannot be determined using absolute age dating. Relative age dating, like we talked about before, does not allow for the determination of an exact age. It just provides an order of what formed first. It is particularly helpful because it requires no advanced technology and can be used on sedimentary rocks. Relative age dating assumes that current geologic processes are the same as those in the past, the principle of uniformitarianism. The principle of original horizontality posits that sediments are always originally deposited in beds that are parallel to Earth's surface due to gravity. The principle of superposition posits that in an undisturbed sequence of sedimentary rocks, each layer is older than the ones on top of it. The principle of lateral continuity posits that layers can be continuous over broad areas when first deposited, but erosion may later remove part of a layer. The principle of cross-cutting relationships posits that layers in a sequence that are cut through by a fault are older than the fault. The layers must have been there for the fault to cut through them. Igneous intrusions also follow this rule. The layers through which a dike cuts are older than the dike itself. Similarly, rock units that are not cut by a fault or intrusion are younger than the fault or intrusion. The principle of inclusions posits that inclusions or clasts incorporated into a rock unit are older than the layer that contains them. This is because the inclusions or clasts must have existed before they could be incorporated into the younger layer. Earth scientists also use clues in the rock layers to determine the depositional or tectonic history of the area. In this case, they're looking for unconformities, a boundary on top or the bottom of a rock layer that is evidence of an erosional surface or a period of no deposition. There are 3 types of unconformities found in the rock record. The first is an angular unconformity, the second is a disconformity, and the third is a nonconformity. An angular unconformity is a boundary between 2 sedimentary layers that are at different angles. An angular unconformity is formed when 1. Horizontal sedimentary rock layers undergo folding, which tilts the layers. 2. Erosion produces a flat surface. And 3. New layers of sediment accumulate horizontally on top of the older tilted layers. A disconformity is a boundary between 2 sedimentary layers that represents a period of erosion or merely a pause in deposition. Layers above and below a disconformity are relatively parallel to one another. A disconformity is formed when 1. Layers of sediment accumulate, 2. Sea level drops and an erosional surface forms, and 3. Sea level rises again and new sedimentary layers accumulate. A nonconformity is a boundary when 2 different rock types a boundary between 2 different rock types, i.e. a boundary between a sedimentary layer and either an older igneous or older metamorphic layer. A nonconformity forms when 1. An igneous or metamorphic body of rock forms, 2. Erosion cuts down into the crystalline rock, 3. New sedimentary layers accumulate above the erosional surface. Now let's try a practice example where we will list the rock layers in this figure from oldest to youngest. The oldest layer in this sequence is layer B. You might be inclined to think that it was A or F, but it can't be A or F because both of those cut through layer B. Next, layer H was deposited on top of layer B, followed by layer K and layer J. Next, igneous intrusion F was emplaced. Then, igneous intrusion A cut through all of those older rock units. Then, layer I was deposited horizontally, followed by layer D. Igneous intrusion E cut through the older rock units but did not intrude into layer G. Layer G was then deposited horizontally, with inclusions of intrusion E incorporated into this rock layer. Finally, rock layer C was deposited horizontally. We have a wonderful example of geologic time here at Ohio State that you might not know about. The first president of this university was Edward Orton Sr. He was the state geologist of Ohio and commissioned the construction of a new geology building, which was later named Orton Hall in his honor. Orton Hall is one of the most iconic buildings on our campus and is even on the National Register of Historic Places. Orton Hall was designed by the famous architectural firm Packard and Yost and was completed in 1893. Orton Hall is the only known building in the world that was intentionally designed to reflect geologic time. Originally, Orton Hall was constructed exclusively of Ohio building stone, which was arranged in correct stratigraphic order. At the base of the building is limestone from the Silurian period. Above this is limestone from the Devonian period. And near the top of the bell tower is red sandstone from the Carboniferous period. And in the uppermost reaches of the bell tower are carvings of Mesozoic and Cenozoic animals. Even the chimes in the bell tower are a reminder of passing time. Currently, Orton Hall houses the Orton Geological Museum, the Orton Memorial Library, and various offices and laboratories. Next, we'll discuss information that you'll need to complete this lab. There are no safety concerns specific to this lab. Be sure to follow the instructions for submitting numerical answers in Carmen. These instructions can be found in the questions themselves. You will be provided with a pair of dice, a decay curve datasheet, and a decay curve graph worksheet. Both the datasheet and the worksheet are available for download on the instruction page of this week's Carmen module. The procedure and worksheets will be provided by your TA, but these will also be available on the instruction page in this week's Carmen module.